In this class, we're looking at example 8 from our physics notes or example 5 from our honors physics notes. And basically, it's the same problem. So more or less what we have is the person picking up a backpack, they carry the backpack and then set the backpack down. So there's 5 distinct phases to this motion. The first phase is where the person picks the backpack up. The second phase is where the person takes that backpack in its lifted position and starts to move it and attains its constant speed. In other words, they have to accelerate it to get it to that constant speed. Phase C is where the person is simply walking with this backpack at a constant speed, and then they're just kind of holding it in their hand or they're on their back or whatever. And then phase D is where the person has to actually decelerate the backpack to stop it. And then the phase E is where they finally set the backpack down back on the ground. All right, so let's take a look. I want to approach this problem in maybe a slightly different way than we have in past problems. And I'm going to do that by, instead of using a familiar equation where the work that we do is equal to a force times the displacement, okay, I'd actually like to look at this from more of an energy perspective, because we know that work, okay, that didn't do what I wanted to. We know that work can cause a change in kinetic energy, but it can also cause a change in potential energy as well. So we're going to take a look at this problem from more of a standpoint of how work can change energy. So this is what sometimes people might refer to as the work-energy theorem. So basically, in my understanding here, I'm not going to draw much in the way of forces, because I'm going to really approach this more from the standpoint of simply energy. So what we're going to do is we're going to ask ourselves about energy at each of these different locations along its path. So again, phase A is where the backpack is lifted. Phase B is where it's getting faster. And then phase C is where we travel at a constant, the backpack travels at a constant speed. And then here in phase D is where the person actually causes the backpack to stop again. And then in the last phase, phase E, is where the backpack is actually lowered. So let's go to each of these positions and talk a little bit about what is happening here. So when I talk about energy, I ask myself 2 questions. My first question is, what is the object doing, and does it have a height? And by what is it doing, I mean, is it moving? So here at the ground, the kinetic energy is found by 1/2 mv squared. Now, it is going to be 0. So basically, my backpack starts at rest. All right. Potential energy-wise, mgh, my initial height, again, it's convenient here, original height, call that 0. So basically, my height is a 0 as well, and that's going to give us 0 potential energy. So my total energy, if I total up the energy here, the total energy is 0 joules worth of energy. Now at the top, we also bring this up to the top and bring it to rest. So again, it's not moving, so therefore it's going to be 0 joules of energy in kinetic. But because we've just raised it, it's going to have some height. And this height, I don't recall what it was. So let's go up and look. I think it was raised to, yep, there it is, 1.4 meters. So that's about the height of a person's back. So this could almost be imagined you're putting on your back. So the height here is equal to 1.4 meters. So that means this value right here, the height is not a 0, it's a non-zero, and so therefore there will be potential energy. So the work that's done, okay, the total energy at this point is just simply potential energy. And again, so the work that we did must have increased the potential energy. So let's actually solve this first part, and we'll come back and talk about the rest of the situation then. Okay, so taking a look at what we know, what we'll see here is that the mass of the backpack is 8 kilograms. It initially starts at 0 meters and it's raised to 1.4 meters high. That is where the work is being done. This is for later in the problem, so let's ignore that for now. This is also for later in the problem, so let's ignore that for now. But basically, our goal is to find the work done for all the different phases. And again, what we're looking at here right now is that first phase where it's being simply lifted. All right, so we have that we're going to use the work-energy relationship. In other words, that the work is equal to the change in energy. So to actually implement that, come over here, and the equation we have is that the work that we do is going to equal a change in potential energy plus a change in kinetic. Now, we did discuss earlier that because it starts at rest and ends at rest, the change in kinetic energy is non-existent. In other words, it's zero. So basically what we end up with is we end up with the work done is equal to a change in potential energy. So in this case, a change in potential energy would be a final minus an original. So mgh final minus mgh original. And do recall that the height originally is actually 0. So pretty much the work we do in this particular case is going to be equal to the basically the potential energy at that second height, that point that we lift it to. So after I substitute my numbers in, the mass of the backpack is 8 kilograms. The gravity, of course, is 9.8 newtons per kilogram. And the height that we bring it to is 1.4 meters. We then multiply those out, and I end up with doing amount of work equal to 109.76 joules. We could just say, if we wanted to, we could round this off to say it's about 110 joules worth of work. All right, let's go take a look at the next phase of motion. Okay, so in this next phase of motion, the object starts at rest and we accelerate it until it has some motion. And I want to say that was 1.5 meters per second. So I believe its velocity at this point in time, its velocity here was 1.05 meters per second. So that means when I ask my question about kinetic energy, is the object moving? Yes, it is moving. So it will have kinetic energy given to us by this equation right here. Also, it will have potential energy, mgh, and since this is the same height, you basically need to know that this is going to be unchanged. Okay, so there's unchanged potential energy because we're not raising and lowering it here at this point. So our total energy at this point is going to be equal to the total energy equals the potential energy plus the kinetic energy, because both of these are a non-zero value. We aren't going to use total energy for this problem, but again, that's going to be an important idea for later on. So I want to introduce that idea. What's going to be important here is the fact that we are changing kinetic energy. So I'm going to go down, come up with a strategy for this, and we'll talk that through. So more or less, we're going to use the same kind of approach here in part B. We're going to use a work-energy relationship to solve for the work that's done. So let's go over and actually implement our strategy. So in this particular case, where we are making this thing accelerate, we are not changing the potential energy. So this change is actually 0. We're not raising or lowering this from its original position. So basically, our work done is going to equal the change in kinetic energy. So again, what that would be equal to is it would be equal to an energy kinetic final minus an original kinetic energy. And once again, since it starts at rest, this is actually 0. Again, you can go back and look at the picture that we drew, but basically the one is 0 and the other is a non-zero. So after I substitute my numbers in, let me scroll this up here a little bit. I'm going to substitute in the numbers for this. I'm going to get 1/2 times mass times the velocity final squared. Okay, don't forget to do the squaring. That's often forgotten. 1/2 times 8 kilograms times 1.05 meters per second squared equals. And after doing the calculations, we end up with 4.41 joules worth of work done to make this backpack accelerate. Okay, let's look at the third phase, which is where the backpack is moved at a constant speed across the floor. So basically, what we're going to look at here is between right here where the object is moving and right here where the object is moving. And again, we ask ourselves our questions. Is the object raised? Yes, it is. It is above the ground, so it does have potential energy. Is it moving? And the backpack is still moving at this point in time, so it has a velocity of 1.05 meters per second. And so therefore, it does have kinetic energy, 1/2 mv squared. So the total energy, again, not used for this problem particularly, but again, I want you to get used to thinking in terms of total energy, is going to be both potential energies plus the kinetic energies. So basically, the same approach applies here. What we want to look is, how did work change the energy that we're dealing with? Well, this value here, because it's at the same height, is going to remain unchanged. Okay, that's going to remain unchanged. And this right here, the kinetic energy, again, it's the same backpack moving at the same speed. So this actually remains unchanged. Okay, now let's look at how this approach works in our equation. So once again, we are going to use the work-energy relationship to solve for the work. So taking a look at how we implement this, what I'd like to remember is that because we didn't raise or lower the backpack during this phase, the change in potential energy is 0. Because we didn't make the backpack get faster or slower during this phase, this is also 0 as well. So the work done during phase 3, or phase, I guess I call it phase C, is actually 0 joules. We haven't changed the energy in this backpack in any way, shape, or form. So we actually do 0 work in this particular example. Okay, so we're going to kind of go through the next two phases here together. But in phase D is where the person stops the backpack, and then phase E is where the person lowers the backpack back to the ground. So let's take a look at this snapshot right here. So again, the object is stopped, so there is no kinetic energy, but there's still potential energy, gravitational potential energy, because it's still raised above the ground, that 0 level that we defined earlier in the problem. Then, to lower it down to the ground, the potential energy becomes 0 because it is on the ground now, and it's also been placed on the ground, so there's 0 kinetic energy as well. So there's going to be 0 energy altogether. So in this part right here, the person is doing work to change the kinetic energy. Notice how these would be the same values here for potential, so the change is only coming in kinetic energy. To lower it to the ground, there's 0 kinetic here, 0 kinetic here. So the change is coming from the change in potential energy from here to here. So let's go down, let's implement this out and see what we end up with. Okay, so once again, to implement part D is where the object is stopping. So the change in potential energy is actually 0, and all the change comes as a result of the change in kinetic energy. So the change in kinetic energy will be the kinetic energy final minus kinetic energy original, and the kinetic energy final is 0 because the object comes to rest. So pretty much what we end up with here is the work done is going to be the energy kinetic original, which will equal 1/2 times mass times the velocity original. And in this phase, the original velocity was 1.05 meters per second. So I'm going to end up with, it's actually going to be negative work here, and I believe it's going to be a negative 4.41 joules. And lastly, our part E is where the object is lowered, so the final potential energy is 0, and all we're left with is the original potential energy. As we calculate that out, we end up with the negative 109.76. So to respond to all the questions, we have our responses here. basically at the beginning we do positive work, and at the end we do negative work, and in the middle we actually do no work at all.